Okay.
So this is the operating principle of many real-time neutrino experiments. And what's shown here is a picture of a research reactor that operates at 500 kilowatts on the Penn State campus. And so this is a picture of many real-time what it looks like when it goes hypercritical, which is scary sounding. Picture of a research reactor, but actually operates at 500 kilowatts on the Penn State campus.
To be safe, but what's really nice is that as a neutrino physicist, you have to provide
when it goes hypercritical,
actually
which is scary sounding.
that are part of several decades.
But actually,
you can actually see this with the naked eye. So you get to see trickle flight that your detectors actually use. So that was almost a religious experience. I recommend it if you can do it. So the detector I'm going to talk about is IceCube. And what's shown here is the present IceCube in the middle of the figure. You don't want to see the speaker. And on the left is what will happen in about a year. And on the right is what we hope will happen in several years, where several could be as long as like 10. So I want to draw your attention first to this region in red on the figure at the right. That's IceCube, and the green inside of that figure is deep core. An IceCube consists of 86 strings, 6 of which are dedicated to deep core, which is at the bottom center of the IceCube detector. The strings are 125 meters apart, mostly. The deep core strings are a bit closer by about a factor of 2. And then in the vertical dimension, the strings are buried under the ice between about 1,500 and 2,500 meters below the surface. And the modules themselves, each of which contain a single photomultiplier tube, are 17 meters apart for most of the strings. And in deep core, they're 7 meters apart. So deep core has a higher density of modules, which means it reaches down to lower energies, as you'll see in the course of this talk. The detector, the large detector, it occupies a cubic kilometer of ice, and it has been optimized for the detection of astrophysical neutrinos at about a TeV energy. In roughly a year and a half, we will be deploying 7 new strings. This is called the upgrade. And these strings will be even closer together than the deep core strings. And that's also true in the vertical dimension, where they will be 3 meters apart instead of 7 meters and 17 meters. This detector is optimized for low energy, where low means GeV scale, 10 to the 9 electron volts, and also to better understand the optical properties of the ice. And if we understand the optical properties of the ice in this region, we'll be able to extend it out to the rest of the detector. And finally, there's what we call generation 2 or Gen 2, which is shown in sort of this bluish green. And this is a detector that's going to, we hope, be built at about 5 to 10 times the scale of the current IceCube detector. So the upgrade has been approved and will be deployed. Gen 2, we haven't yet applied to get funding for that detector. And just in case you're wondering, I have been to the South Pole. It is cold. So it was like minus 60 centigrade with wind chill. That smile there was frozen on my face. The neutrinos that we look at in IceCube come from primarily atmospheric and astrophysical sources. Neutrinos, of course, have a wide range of energies, ranging from the micro electron volts all the way up to eta electron volts. We're going to focus on this region here between about 10 to the 10 and something like 10 to the 15 electron volts. The challenge that we face in looking at astrophysical neutrinos, which is this sort of magenta line towards the right of the plot, is that in 10 years of data, we have something like 10 to the 12 triggers, most of which are downgoing cosmic ray muons. And out of that gigantic number of essentially useless background data, we have to extract 10 to the 6 atmospheric neutrinos and something like 100 to 1,000-ish astrophysical neutrinos. So it's a small needle in a very big haystack, if you will. So the atmospheric neutrinos are produced when cosmic rays hit the atmosphere and produce a shower of particles. There are neutrinos in that shower, and those neutrinos can make it all the way through the Earth. And that's what's indicated here in this figure. Neutrinos that are produced, in particular muon neutrinos that are produced in the northern hemisphere can oscillate into muon neutrinos. Sorry, muon neutrinos can oscillate into tau neutrinos. And in fact, at roughly 20 GeV, a muon neutrino that's produced in the northern hemisphere and travels at the North Pole, I should say, and travels directly through the diameter of the Earth, has nearly 100% probability of oscillating into a tau neutrino. And then it goes down from there. So we see neutrinos coming up in the detector. They have passed all the way through the Earth. So the Earth acts as a filter for everything else that isn't a neutrino. We can also, of course, detect neutrinos that are coming down on our detector from above the experiment. And the energy range that we look at here is above a GeV, more than 10 to the 9 electron volts, up to about a TeV for studying atmospheric neutrinos. On the other side of the energy scale, IceCube is also sensitive to astrophysical neutrinos, where these neutrinos are, we believe, created in places like active galactic nuclei, where there are particle jets created by infalling matter around black holes. And here we see these neutrinos at energies above about 50 TeV. And we've also seen them at even higher energies. In fact, we've seen one at about 6 times 10 to the 15 electron volts at what's called the Glasgow resonance. And this figure here at the bottom right is an artist's conception of what one of the sources that IceCube has detected called the Texas source, TXS 0506 056. Doesn't really have clouds around it, but it looks kind of impressive. So let me start out at the low energy scale with atmospheric neutrinos. The motivations for studying these neutrinos is to understand the properties of these fundamental particles with high statistics and in an energy regime that's much higher than accelerators or reactors can attain. So we can look at muon neutrino disappearance, the related tau neutrino appearance, and also, in principle, the neutrino mass ordering. So the events in the deep core experiment at low energies don't produce a lot of light. And you can see that in this event figure at the lower left. And this particular event had 3.6 GeV, and it produced 2 photons. So you're not going to be able to do very much with that. At 21 GeV, this is a tau neutrino that has interacted. These are both simulation. And you can see that it produces, 10 or 20 photons that can be detected. So that we can do something with that. But obviously, in such a sparse detector, the neutrino flavors are going to be difficult to distinguish one from the other. And generally, in these kinds of figures, the little dots here, we can blow up this a little bit, make it a little easier to see. The little dots are individual modules. So they each have a 10-inch photomultiplier tube inside of them. And the circles in colors indicate that that module detected 1 or more photons. The size of the circle is going to be proportional to how many photons it saw. And the color is proportional to the relative time at which the photons arrived. And that goes according to the colors of the rainbow, starting with red and ending with blue. And so this green, this module here, looks like it got probably 2 photoelectrons at a different time from the other number of modules. And you'll see some more colorful figures coming up. So here's our most recent result with atmospheric neutrino oscillations using a little more than 9 years of deep core data. And what we did was we split the sample that we got into 3 different types. One that was very cascade-like, so it looks like a shower, and it produces a spherical light pattern in the detector. And then at the other end, in the bottom plot, is shown track-like events. And then in the middle is where we couldn't really decide what it was, so we just put it in the middle. So we have in these figures, let me just blow this up so you can see a little better, all the different contributions to the plot. But I think the thing to notice is the prediction in this dashed line is what you would get if there were no oscillations. So no oscillations of muon neutrinos into something else. And underneath that is what you expect with oscillations, and you can see that the data is very consistent with there being oscillations. And that's particularly pronounced, well, it's pronounced in all these channels. And ultimately, what you end up providing for the neutrino oscillation community is the figure shown there at the right, which is the delta m squared between the 2 neutrino mass states and sine squared theta 2-3, the mixing angle. And the dark line, the dark contour, is this result. And the results from other relatively recent experiments is shown as well. And you can see that the IceCube result is quite competitive with these other experiments. And I want to add that IceCube was not designed originally to do this kind of physics. The fact that it can address this kind of physics just speaks to the power of building sort of a flexible detector that has the option of doing lots of different things. So as I mentioned earlier, we're going to put in several new strings called the IceCube upgrade. And this is kind of a blow up of what you saw before. So these red dots are the new strings that we put in. The green dots are the existing deep core strings. And then the black dots, the smaller ones, are the regular IceCube strings. We call the existing detector IC86, IceCube 86 string. And then when we add 7 new strings, IC93, these modules are going to have between 5 and 10 times more denser spacing. 750 new modules are going to be deployed, about half of which are going to look a lot like the modules for KM3net. I'm sure you're familiar with those. That's an experiment that's going to be built, or is being built, in the Mediterranean. The idea is to collect more light and to better calibrate the optical properties of the ice. And it will be deployed, as I mentioned, in a short time, in about 1.5 years. So this is that figure I showed you before. This is with IceCube 86. And now if we do the same, look at the same events, but with the upgrade modules added, this is what we'll see. So you can tell that the number of photons we're going to collect is going to be much, much higher. And even though by eye, looking at these two events, it's hard to tell that this is a shower and this is a track, algorithms that we write can relatively easily tell the difference between those two topologies, even though to the eye they look quite the same. And I apologize that all these colors are the same in these figures, are very close to being the same. We need to figure out how to shrink the time window so that the colors are more evenly distributed across the rainbow. You'll see when I show you some higher energy events that they're more colorful and pleasing to the eye, as well as more informative. So what can we do with the upgrade with neutrino oscillations? So what's shown at the bottom left is that delta m squared versus sine squared theta 2-3 plot, but now with the projected sensitivity of 3 years of upgrade data added to the deep core data that we'll have by that time as well. And you can see that contour, this black contour, has shrunk quite a bit. So this is going to be a very competitive result. And so you can expect that in something like 4 years from now, 5 years from now. We can also measure, I should say remeasure, tau neutrino appearance. So this little figure here with the orange, green, and blue bars shows the existing measurements of this quantity. And I remind you, this is the result of muon neutrinos produced in the atmosphere and traveling through some fraction of the Earth and oscillating into tau neutrinos. So what's shown plotted here on the x-axis there is the ratio of the measured flux of tau neutrinos due to oscillations versus the expected number of tau neutrinos. And so what you would expect if the standard model of oscillations is correct, that these would lie right at 1.0. So Super K has measured a value that's at 1.4, which is kind of hard to interpret because it seems to like violate unitarity, but there's a big error bar. Opera likewise, Deep Core with 3 years of data has measured something like 0.7 with an error bar that's about 30%. That will shrink dramatically once we include upgrade data and redo this measurement for tau neutrino appearance down to something like plus minus 5% error bar. So if we continue to measure, as shown in this orange data point, if we continue to measure something like 0.7, but now have an error bar that's 5%, we will be saying effectively that these muon neutrinos are oscillating into something in addition to tau neutrinos that we're not seeing. So for example, sterile neutrinos. So we'll be able to test the standard model of neutrino oscillations quite stringently with that kind of measurement. We will also have sensitivity to the neutrino mass ordering. And for those of you who are not familiar, so the neutrinos have masses that are basically aligned like my fingers shown here. All we know is the difference in the mass squared between the masses. That's what's between the neutrinos. That's what's measured. And we don't know if the neutrinos are oriented like this or like this. So this is the normal ordering, where there's one neutrino that's pretty high up and there's other two neutrinos that are close together in mass. Or it could be like this. That's called the inverted ordering. And we can measure that by looking at these oscillations that occur in the Earth's core. So there are matter effects that occur there. This is a very difficult measurement. And in fact, even with the extra modules that'll be part of the upgrade, it's going to be very hard for IceCube to make a statistically significant measurement of this. And that's particularly true, as you can see from these figures, which show, if you focus on the left-hand side first, that top plot. So this shows how well we can exclude the inverted ordering if the normal ordering is true. And what the top figure shows is, as a function of this mixing angle, theta 2,3. A minute. That's not what I wanted it to do. Now it's getting very confusing. Thought I had a way to fix this, but I seem to only be able to make it bigger. So there we go. Anyway, you can still kind of make out that the current favored value for theta 2,3 is at the wrong place. So this is where we have the least, almost the least sensitivity to the ordering. So let me see if I can go back and come back to this slide. Maybe it'll fix itself. No. I apologize. Thought I knew how to undo this, but wait a minute. There we go. Hold on. Almost. Yes. And then this lower plot here, I'm going to try again. There we go.
This lower plot shows what the sensitivity is in sigma as a function of lifetime in years after we've deployed the new strings, which is right here. So this is after 12 years of deep core data. And then you can see that the sensitivity grows dramatically with the addition of the new strings from the upgrade. But even then, we'll get very, very lucky if we can reach even just 3 sigma with our detector. And it's even worse for the inverted ordering, which you can see in the lower right. There, we're getting lucky if we can see it at 2 sigma. However, don't despair. If we join forces with Juno, which is a reactor experiment, and make the measurement or use their measurement and our measurement and play them off against one another, even if we only reach like 2.5 sigma with the upgrade data, combined we can reach 5 sigma with Juno data, even if that's only at 2 or 3 sigma. And there's a complicated reason for why that's true, and I can refer you to the literature to understand why that's the case. And by the way, the same is true with the ORCA experiment. ORCA can also join forces with Juno. Hopefully, all 3 of us will get together and make a definitive measurement of the neutrino mass ordering. Okay, so let me now move to the higher energies and talk about astrophysical neutrinos. So we've opened effectively a new window on the universe by looking at energies of neutrinos above about 10 to the 12 electron volts. And I think that's illustrated by this plot here, which shows the distance on the y-axis in megaparsecs versus the energy in electron volts. And what you see is that there's this region that's sort of shown by that scary sort of black blob that is opaque to photons. And that's because photons at those high energies interact with ambient infrared photons and also the CMBR and end up being absorbed effectively because they get converted into E plus E minus pairs. But that region, that energy region and distance region, is transparent to neutrinos. Neutrinos can make it through all that, whereas the photons can't. So when you start looking at this region of distance and energy, you are opening a new window that can't be seen electromagnetically. And here's what IceCube has seen since it started operating a little over a decade ago. This is just to sort of orient you. So we built the detector, or finished building it in 2011. That's just here. And then a couple of years after that, we discovered astrophysical neutrinos, but we didn't know where they were coming from, or we couldn't pinpoint their sources. So we called them diffuse neutrinos. And we had a clear excess of those neutrinos above the atmospheric background. So that's what's shown here in those data points. And then 5 years after that, we detected the Texas source. This was a multi-messenger campaign in conjunction with the Fermi telescope. The Fermi satellite experiments saw the Gamma Ray Observatory saw a gamma ray that came from the same place at roughly the same time as a very energetic neutrino seen by IceCube. So that was the first source that we detected. A few years after that, we detected a very energetic event, 6.3 PeV, 10 to the 15 electron volts, consistent with a glass-shell resonance event. Glass-shell resonance event is when an anti-electron neutrino interacts with an electron to produce an on-shell W boson. And that happens at 6.3 PeV. There's a big peak in the cross-section there. And so we had an event that was consistent with that energy. So in principle, that's the first detection of a flavor of neutrino other than muon, first definitive detection. We found a second and a third source. We found in a year after that, NGC 1068 as a
as a strong emitter of astrophysical neutrinos. And then a year after that, we found neutrinos coming from the galactic plane. Talk more about that in a minute. And then this year, just recently, we published the detection of 7 astrophysical tau neutrinos with a significance that's above 5 sigma. Okay. So why are we looking for astrophysical neutrinos? There are a few obvious motivations for doing this. We could be quite happy just looking at atmospheric neutrinos, but atmospheric neutrinos, astrophysical neutrinos open a new window, as I showed you with that previous plot. We hope to uncover the production mechanisms. Is it just pions that are decaying, or is there some strong magnetic field at the source that's causing other things to happen? Based on what we detect here at Earth, we can say something about how these incredibly energetic sources are behaving. We can also study the properties of the neutrinos themselves as they propagate over extremely long distances and at the highest energies available. And in so doing, we'll gain sensitivity to new physics. So here's what these more energetic events look like. And now the colors, hopefully, are more impressive. So starting at the left, this is the topology that a very energetic electron neutrino might have. So you can see that there's a lot of light deposited on one module, big blob here, some larger blobs over there. And as I mentioned before, the colors indicate the relative time of arrival, starting with red and going out to blue and green. And you can see that this event started in the middle and then expanded out. So it's basically like a ball of light. But we can extract some directional information from these events. It's not completely isotropic. In fact, we can point back to the neutrino direction to about 10 degrees at 100 TeV. Of course, we make a pretty good measurement of the energy, especially if it's contained in the detector, something like a 15% measurement. The other main signal, and in fact, the first one that we, signature, I should say, and in fact, the first signature that we looked at in IceCube was that due to muon neutrino having a charge current interaction that produces long muon track. And this muon track can go literally for kilometers. And what's shown here is one that enters the detector over here on the right, and then travels all the way through the detector and exits on the left. So we get really good pointing with this, and the pointing, when we consider really good, is still like laughably large for astronomers. So 0.1 degree is still kind of big. But 0.1 degree is not so big that you can't, give it to an astronomer and they won't, and have them just laugh at you. Like they can't possibly tile the sky at 10 degrees with the cascade over there. But for a muon neutrino, 0.1 degrees is plausible. And in fact, this is what we use to find the first source, the Texas source. Getting the energy of these events is a little bit trickier because we don't know where they started. Could be way over here on the right, and we don't know how far they go on the left. And when they're going through the detector, they could have stochastic deposits of energy that make them look more or less energetic than they actually are. And finally, there's the tau neutrino. When a tau neutrino interacts in a charge current interaction, it produces an initial cascade from the W boson that is emitted. So that's what you see down here in red. This is a simulated event. And then if it has a lot of energy, the tau lepton can then travel an appreciable distance in the detector. And it will then decay. And most of the time when it decays, it will produce a second shower. So that's shown in green in this figure. And there's a little bit of light produced by the tau lepton itself as it goes between its initial production point here at the tau neutrino interaction vertex over to its decay point. but that's negligibly small compared to the energy that's deposited by these showers. And what's shown here is what's colloquially called the double bang event. You have one cascade here, bang, another one there. So at these energies, in principle, the flavors of the neutrinos can be distinguished from one another. But up until very recently, IceCube has mainly focused on muon neutrino charge current events. That's identifiably due to a muon neutrino, because it's a big, long muon track. It could be due to a tau neutrino, where the tau lepton decays into a muon, but that doesn't happen very often. And everything else was a shower. So any neutral current interaction of any flavor neutrino produces a shower. Electron neutrinos will produce a shower because the electron is confined to a small region, dumps all its energy there. And most tau neutrinos will also produce one shower, because the tau lepton at lower energies may only travel, centimeters or a few meters in our detector, and our detector cannot distinguish these two showers here if they're right on top of one another. So these events are pretty large, and I just wanted to remind you of that by putting one of our events next to a familiar object. So they're big, hundreds of meters, sort of in radius. But there's still background, even though you think something that large would be easily distinguishable from something else. Because in IceCube, we have this enormous rate of downgoing muons, 3 kilohertz, and a much lower astrophysical neutrino rate. So there are three ways that we can reduce the backgrounds primarily from downgoing muons. So the first thing we do is we look for events that are going up in our detector, and that uses the Earth as a filter. And that means that it had to be a neutrino. So that's what's illustrated in the lower left here. And this has the advantage that the neutrino purity is unquestioned. It has a disadvantage that at really high energies, the Earth doesn't just filter out other stuff, but it also starts filtering neutrinos, because neutrinos start to interact in the Earth once they reach energies of about 10 to 100 TeV. So you can't see a PeV neutrino that was produced in the northern, at the North Pole going all the way through the Earth. It'll get absorbed in the Earth before it gets to the South Pole. I turned the Earth upside down for purposes of this discussion here. The other thing we can do, if we want to look at events that are in the southern hemisphere going down in our detector, is we can define the outer region of our detector to be a veto region. And we can say that we don't want any light to be deposited in that veto region before light appears in the inner fiducial region of the detector. So this is what a muon would do on the left of this figure. So it produces some light here in the veto region first, then goes through the detector. We don't want that. We have too many of those, and they're useless. Not totally useless, but not as interesting as neutrinos. On the other hand, if a neutrino, a muon neutrino interacts inside the detector, then the first light that you see will be in that region. Some light can then travel out into the veto region, but it will be later, because it has to travel a fair distance, than the early light that is produced right after the muon neutrino interacts and produces a muon. So these are called starting events. The other possibility down here at the bottom is to identify sources. So if we can see multiple neutrinos coming from the same place in the sky at roughly the same time, that's a great way to get rid of both atmospheric neutrino background and cosmic ray muon background. Or we look for neutrinos in coincidence with other observatories, such as the Fermi Gamma Ray Telescope. So let me now give you what the current picture is for diffuse astrophysical neutrinos. So our starting sample here is about 700,000 events after a lifetime of 10 years. and roughly 1,000 of those are astrophysical neutrinos. And you can see in this plot here, in this region, that there's a clear excess of neutrino events at high energies. I don't think it was my pen that did that, something else over here. At these really high energies, there's an excess of neutrinos above what you expect from the atmospheric neutrinos. So there's about 57 events over here. They are consistent with a flux that varies as with a spectral index of 2.3, minus 2.3. One thing that you can't tell from this plot, but we have observed, is that the flux of astrophysical neutrinos is larger than the flux of gamma rays at these energies. And presumably the reason for that is that the gamma rays lose energy in these dense regions around the sources where they are presumably co-produced with the neutrinos, but the neutrinos just whiz right out. They don't lose any energy. So seems to be a consistent picture. We have a new channel that we just recently opened, which involves using starting tracks instead of tracks that are going through the detector. And this allows us to go down lower in energy using something called the self-veto. So the self-veto is a way to remove atmospheric neutrinos that are coming down through the detector. And this is an advantage. We can't do this for neutrinos going up through the detector for the following reason. When a neutrino is produced in the atmosphere and goes down through our detector, it is very often accompanied by a muon. And you can see that muon, and so you can veto that event. So any neutrino that is downgoing in the detector, not accompanied by a muon, is very likely astrophysical. So we can reach down to roughly a TeV, and this figure here shows the flux versus the neutrino energy, and we go down to roughly a TeV in energy now. The index for these neutrinos is similar to the one shown previously. It's a little bit different, minus 2.3, a little bit, 2.6, a little bit softer. The average pointing resolution on these neutrinos is a bit worse because the energy is a bit lower. But the spectrum is compatible with our previous results. And in particular, there's no evidence of spectral hardening, which might indicate that there's multiple kinds of sources producing these neutrinos at low neutrino energies. We also see astrophysical neutrinos as showering events. So here again, we don't have very good pointing, but we have good energy resolution. And as of 2020, we had this magenta region here, which had a spectral index of 2.5. We added an event in 2021. This is in fact the Glasgow resonance event. You can see it has roughly an energy of 6×10⁶ GeV, which is where the Glasgow resonance is. And you can see that this result is also consistent with the previous results, which were using muon neutrinos. Now we're using other neutrino flavors and neutral current interactions to make this measurement. So putting it sort of all together, here's the flux plotted against this the spectral index, gamma. And you can see that with multiple different analyses listed over there on the left, we are, first of all, self-consistent, and we're seeing sort of a spectral index of around 2.5 and a flux given in those units at around 1.5 or 2. And this is over a range in energies of 3 to 550 TeV. So a couple orders of magnitude or more in energy. And there's no evidence in any of these studies for a spectral break. A single power law seems to suffice to explain all the data. There's also no evidence for prompt atmospheric neutrinos. So there's a distinction drawn between conventional and prompt atmospheric neutrinos. Conventional atmospheric neutrinos are produced when pions or kaons decay in the atmosphere after being produced by a cosmic ray interaction. And the prompt neutrinos are produced when charm is made in the atmosphere and decays very quickly and produces more energetic neutrinos. So we also have detected some point sources. We see them mainly from active galactic nuclei. And what we're using are, again, muon neutrinos, because these have subdegree pointing. We found, for example, 80 events within about 0.2 degrees of NGC 1068. And so you see in this all sky search, the most significant point is NGC 1068. And then there are two others that have also been highlighted. And this is a blow up of what that looks like. So we found sort of 80 events within a very small error region of the position of NGC 1068. That's our hottest spot in the sky. We also have used astrophysical neutrinos that don't produce tracks, but produce cascades by using a deep neural network to improve the pointing by about a factor of 2 on what we had before. And by doing that, and then looking at the galactic plane, we were able to add this panel down at the bottom to this iconic set of pictures of the galactic center. So this top row here is the optical view of the galactic center. And then there's gamma rays here. And then the middle row is what you would predict in neutrinos if you had perfect resolution on the pointing and a particular model, the so-called pi0 model. And then the bar just below it is what we would expect after we go through our analysis and we smear out the directions because our resolution is certainly not perfect. And then finally, down at the very bottom is what we actually measure. And we were able to exclude the possibility that backgrounds are mimicking what these 3 different models. That time I stepped on the cable. Sorry about that. Sorry, good. So we're able to exclude these 3 different models at nearly 4 or 5 sigma. What's interesting is when we compare these galactic neutrinos to what comes from elsewhere, we observe that only about 10% of the neutrinos in our total flux are coming from our galaxy. So the other 90% are produced by powerful accelerators that are much farther away. And that's what's shown in this figure. These 3 colored bars are from the galactic center, and each color corresponds to a different model. And then the all sky flux is shown as the higher flux, about 10 times higher in the hashed. Okay, so for the end of this presentation, what I'd like to do is tell you about flavor physics at astrophysical energies. So none of the previous results explicitly identified tau neutrinos. At atmospheric neutrino energies, the tau neutrinos are indistinguishable in our detector from other flavors of neutrinos. But at astrophysical neutrino energies, they can be distinguished. In fact, though, tau neutrinos can also mimic muon neutrino interactions if the tau decays into a muon, or electron neutrino if the tau lepton doesn't have very much energy and decays very quickly. It can look like a single cascade, or it can look like a track. But there is a region in between where it can look like something that isn't track-like and that isn't single cascade-like, and that's what we're going to focus on. So if you assume standard neutrino oscillations over astrophysical distances, you predict roughly a 1-to-1-to-1 flavor ratio at Earth. So what you expect most of these sources are producing is a flavor ratio of a 1-to-2-to-0, nu e to nu mu to nu tau. Because when a charged pion decays, that's what comes out. Charged pions are presumably what's being produced far away when protons that are accelerated smash into some stuff surrounding a black hole, pions come out. And then they decay into, among other things, neutrinos. By the time these have traversed all the space in between us and the source, there should be numerous tau neutrinos in the beam. So these tau neutrinos should be in our data. That flavor ratio can be somewhat altered by the production mechanism, just by a little bit, but it can be dramatically altered by new physics. So since I'm running low on time, I'm not going to spend as much time on this plot as it deserves, because it's kind of a very information-rich plot. It shows the fractions of the three different flavors that you expect on each of the three axes, nu mu, nu e, and nu tau. And the contours show how well we're going to narrow down on the flavor ratio with experiments as experiments improve and have more data. And the time scale here is roughly today and roughly 15 years from today. So those contours shrink. And then the colored regions show you how well we will be able to predict what the flavor ratio should be at Earth based on measurements from accelerators and reactors of the neutrino oscillation parameters. And the blobs are how well we can do now. So that's sort of the uncertainty. And the dots in the center is how small those uncertainties are going to be once we've had more data in about 15 years from a variety of experiments like Juno and Dune and hypercandiocombinate. And the different colors correspond to different possible ways that neutrinos are produced at these sources. And so the takeaway message here is that with improved measurements of the oscillation parameters and improved measurements of the flavor ratio with experiments like IceCube, we'll be able to narrow down on how I should say, these neutrinos are being produced at these sources. On the other hand, if we find that we don't have one particular flavor and only other two, it could be an indication that something strange is happening in between the source and us. And in principle, something like quantum gravity could be detected by observing that the flavor ratio is far away from what we expect. So in order to identify tau neutrinos, you can look for them inclusively or exclusively. So inclusively means you look at a bunch of data and you see which ones look more like tau neutrinos than something else. And exclusively means identify them one by one in your data set. The challenge here for finding, say, the double bang event, which is this one, that's what you look for first, because that's blaringly obvious, is that the tau lepton travels 50 meters for every PeV of energy. So you need, in order to separate two cascades like this in the sparse detector like IceCube, you need energies of order several PeV in the incoming neutrino. And those are exceedingly rare. And furthermore, you need that neutrino to interact in just the right way so that both of the showers are contained within the detector. So basically, the upshot is there's really very limited phase space for this kind of event. And so we don't detect. We haven't detected any of them yet. If you go down to lower energies, though, the two cascades produced by the tau neutrino are closer together. And so I put together this animation with the help of Dr. ChatGPT 4 to show you what happens when two showers produced by a tau neutrino, one after the other, the first one being red, and then the next one being blue, wash over a single string of IceCube modules. Each circle here represents a module. And what you should see, I hope, is, first of all, I am a brilliant animator. And secondly, that the light washes over these modules, first hitting this module, the red, and then this module here, these two modules above, and then the two modules above that. So it sort of spreads out along the string. And then sometime later, you get the light from the blue. And I've made these rings get wider and wider and also fade as a way of sort of mimicking the ice properties. They're going to be absorptive and also scattering. Of course, these interactions can occur with a variety of orientations relative to the string. And that's sort of shown by these 5 different possibilities here. Of course, there are lots of possibilities. And each of those produces a different signature from the other. So we did an analysis a while ago with an inclusive channel looking for events in 60 well-contained high-energy events that in a sample that already existed, and we were confident had high astrophysical purity. These are called the HESI events, or the high-energy starting events. And what we ended up doing was classifying these events as being mostly single cascade and tracks, but 2 of the events were more consistent with from the fit that we did on this data to a double cascade. And here's one of these events, which we called, not so cleverly, double-double. And what you can see, and this is sort of the standard display I've been showing you before, but on the sides are individual waveforms of the light arrival as a function of time in these modules. And you can see, I hope, that some of these have this sort of double peak structure, where one peak comes from the light from the first cascade, and the next one from the second. So with these 2 events, but with a fairly large background, we were not able to make any strong claims about the existence of tau neutrinos. We could exclude the null hypothesis of no astrophysical tau neutrinos at 2.8 sigma. How much time? Okay. So in order to improve the situation, what we did was instead of doing a fit, and instead of looking for individual modules that had a double pulse signature, we said, well, why don't we try to look at more modules? And so what we did was decided to look at 3 strings, one that had the highest charge, and then its 2 highest charge nearest neighbors. And then we made these plots, these figures, images, if you will, that show the DOM, the module index. So that's on the y-axis, and that's proportional to the depth versus the time on the x-axis. And so if you go horizontally, just choose a line here like that, what you're seeing is sort of a waveform that's been rendered by the colors. So the brighter the color, the more light, and as a function of time across the x-axis. So you basically have a whole bunch of waveforms sort of in this one image. So it has the raw data in it effectively. And hopefully you can see that there are 2 hyperbole there. You remember when these expanding these expanding light spheres pass over modules on a string, they would produce a pattern that's hyperbolic as time evolves on the x-axis, and as you go to higher and lower z positions on the y-axis. Okay, so hopefully that's clear what those images show. And down below, the row below shows individual waveforms in a selected few modules. And you can see in this simulated event, for example, that waveform looks like it has double pulse in it. So that's what we sort of focused on initially, is let's find more of these double pulses.
And rather than trying to look for them with our eyes or a specific algorithm, we decided to use convolutional neural networks. We took those 3 images and we trained them using an existing neural network called VGZ16, which is very good at visual image distinguishing. And we did that actually 3 times. One time trying to distinguish tau neutrinos from, say, electron neutrinos, and then another time tau neutrinos versus downgoing muons, and then a third convolutional neural network, tau neutrinos versus astrophysical muon neutrinos. So we had 3 different neural CNNs, convolutional neural networks, 3 different scores that we could then use. And we applied those cuts on those scores in order to select our signal from our background. And when we moved from a set of basic cuts that we made, essentially asking that the event look more like a cascade or a shower than a track, and that it had a certain amount of light and so on, we moved from a signal to noise of 0.003 to a signal to noise of 14 after applying these CNN cuts. And this figure here shows one of the scores in a cumulative plot at values below the value that we use. You can see there's pretty good agreement between the data and the expectation from backgrounds and signals. And this is what we expect the tau neutrino energy spectrum to look like. So what's shown in these 3 different colors are the tau neutrino, expected tau neutrinos and expected backgrounds from astrophysical neutrinos of other flavors and atmospheric neutrinos. And what you can see is at the final cut level, which is a solid line, the peak is at about a few hundred TeV. So that's where we expect to see most of our events. The ratio plot down here shows that, in fact, this analysis would really like to see very energetic neutrinos, tau neutrinos, if they were there. So we do have sensitivity to those very energetic neutrinos. So here's what we expected to see in our signal and our background for 2 different IceCube measured fluxes. So our expectation for signal and background depends on which flux we assume. And there are 4 different fluxes that were available at the time this analysis was done. And here are the initial and final numbers of signal and background events for those 2 fluxes. One flux is called global fit, and the other one in parentheses is Hesse, assuming 9.7 years of lifetime. And you can see that there's a big difference, first of all, between what we get at the initial cut level and then what we get after we apply the CNNs at final cut level. And secondly, that the biggest contribution to the background is other astrophysical neutrinos, 0.3 events. We expect somewhere between 4 and, in this case, 6.4, but in fact, depending on the flux, it goes as high as 8. We also expect contribution from atmospheric neutrinos. Prompt atmospheric neutrinos haven't been measured yet, but we assume that they were there to be conservative. We also did not include the self-veto effect that I mentioned before, which means that both of these numbers should actually be smaller. So that's, again, conservative. So the total amount of background here is about 0.5 events, and the signal is about 6.4. When we opened the box, we saw 7 events. 4 of them are brand new, 3 events we'd seen before in other analyses. Shown in this figure is the score C3 versus the score C1. And what we did was we broke this up into 16 bins and then calculated our significance using the expected background in those bins. And what you see here is that 2 of our events were located in the second best bin, and 5 of them were in the best bin, which had the farthest way up in the corner of C3 versus C1 space. We can calculate something called the taunus,
which is the number of signal events expected in bin I, divided by the signal plus background expected in bin I. And all of our events have tau that's greater than 90%. So they're pretty likely to be tau neutrinos. So assuming the global fit flux, which gives us our most conservative result, we can exclude the absence of astrophysical tau neutrinos at 5.1 sigma. So this is, if you will, a discovery. It's a little bit strange to call it a discovery just because we expected them to be there. So you don't discover something that's expected. But some people say, yes, it is a discovery because it's 5 sigma. You set out to look for something, you found it. So anyway, that's a linguistic issue. I'm not going to go into that. The other fluxes from IceCube predict higher levels of significance, slightly higher. You could also look at this as a 40% level confirmation of the standard model of oscillations, because square root of 7/7 is about 40%. It's certainly a powerful confirmation of IceCube's earlier discovery of diffuse astrophysical neutrinos, because atmospheric tau neutrinos are negligible at these energies. They don't exist at these energies. So the neutrinos that we saw, the tau neutrinos we saw, had to be astrophysical in nature. Okay, almost finished. So I can't just leave it there because this is a high significance measurement. We need to be sure that we're actually not fooled by some background. So we did a number of tests and studies. We, of course, looked at the events, and we did something called making saliency maps to see what the CNNs were doing. And we did a variety, we reconstructed the events to see that they were consistent with expectation. And we did a variety of tests of the CNN scores for their robustness, and doing something it's called deep fool, which is a way you can try to manipulate your image to fool the CNN. We did all these things, and the upshot is that the CNNs are sensitive not to the double pulse structure that might appear in one or more modules, but more to the overall event structure. The reconstructed distributions look fine. By varying the light levels manually, the migration from signal to background or background to signal was small and consistent with what we expected. The scores themselves were very robust. Only like really serious alterations in the images that were well outside of systematic expectations could make things change. So here's one of the events we saw. So we recovered double-double, which was gratifying. And you can see like module 26 on the first string there has a double pulse structure. So we were happy. We sort of thought we found what we were looking for. And then we looked at this event, which is called barn owl. Since we discovered some events, we were able to give them our own names, and we chose the names of rare birds. And we were squinting a lot with our eyes to try to see a double pulse structure there, and really couldn't see it. And so we started scratching our heads and saying, well, what are the CNNs actually doing? And in order to answer that, we applied something called saliency maps, and use images of dogs and cats to illustrate that. So you take a whole bunch of images of dogs and cats, labeled as dog and cat, and you make a convolutional neural network. And then you can take fresh images of a dog and a cat, and you can produce these saliency maps, which basically say, what is the CNN most sensitive to? Which pixel, if you change it, would change the score predicted by the CNN the most? And so what you can see is, well, the dog's eyes are pretty important. The snout is pretty important. The cat's ears are pretty important. And also, because you can't tell cats what to do, most of them sit on tables. And so if there's a table in the picture, it also highlights that. So this is sort of a cautionary note that you have to be careful when you're using these kinds of tools, that you don't get fooled by something like that. Now, physicists who can simulate data don't really have to worry about, cats sitting on tables mimicking or fooling the network into thinking it's a cat, because in principle, you could probably put, some other creature up here on a table, and this network might say it's a cat. But because we can simulate our events in large numbers, and we know exactly that each one is a tau neutrino or a muon neutrino, electron neutrino, we don't have this concern so much. So if we make a saliency map of barn owl, what we have is, so this top row shows what you saw before, column number versus time. And then the bottom row shows the saliency maps. The black lines, contours, show where the light level goes to 0. So it's basically an outline of the figure above it. And then what you see is where there's a lot of light, so inside the contour, there's a strong contribution to the score, CNN. But where there's a high saliency, where changing the light level matters, is at the leading and trailing edge of the light. So that's right along here, where the contour is showing there's 0 light. So we're not so sensitive to the double pulse structure, but more to the overall structure of the event. And very quickly, here's the energy and the reconstructed zenith angle, consistent with our expectations. The energies are at about 100 TeV, as we expected them to be. So I'll conclude now with what's next. So with the atmospheric neutrinos, we expect with the upgrade to have leading sensitivities to muon neutrino disappearance and tau neutrino appearance, and sensitivity to the neutrino mass ordering, particularly in conjunction with Juno. In astrophysical neutrinos for tau neutrinos, this analysis that I just presented used only 3 of 86 strings. More strings would allow us to reduce the background, improve the background rejection, so we could relax the cuts and increase the signal level. And possibly we can start to rule out some astrophysical source types models. And we also are working on applying a dedicated reconstruction to the tau neutrinos in order to get their direction and their energies better. We could start looking for point sources that are producing tau neutrinos. And we can study the parameters of the tau neutrino and the tau lepton at unexplored energies. More generally, for astrophysical neutrinos, in the diffuse case, we will be able to improve our sensitivities by using better reconstructions, of course, more data, and by combining analyses across various channels. And we're going to continue to test for unusual spectral features in the data. In the point sources, we'd like to know, are there sources other than active galactic nuclei producing neutrinos, galactic plane producing neutrinos? We have a number of active multi-messenger real-time searches going, and they will continue, and something can happen at any moment. And with the upgrade, we're going to improve the ice properties, our knowledge of them, and that will give us better pointing, not only for data that we take in the future, but also data that we already have in the camp. So archival data will also be improved. There are future detectors that are online or going to come online. For example, KM3net and P1 in the Pacific, which have less scattering of the light produced by neutrino interactions, which translates to a larger effective volume per string for tau neutrinos, which means that it should see more neutrinos for more tau neutrinos for a given detector size compared to IceCube. And also these will have detectors will be situated in the north, so it'll have enhanced sensitivity to the southern hemisphere and in principle better pointing. And finally, Gen 2, when it comes online, will have something like 5 times the volume of IceCube. So neutrino astronomy has definitely begun, and these cubic kilometer detectors are sensitive to fundamental neutrino properties. So thank you very much. And I apologize for going so long.
Thank you. Do you have questions for me?
I'd like that you comment a little bit more on slide 21. I mean, if I understand, there is quite a lot of events about the PV region, and I mean, it's not clear what they are. And
Well, there's really only one event that's at that
what
scale.
are the other dots
These are all limits.
of the green one? Okay.
This is the only data. Yeah, the green ones are limits from previous analysis.
This is the glass shell event here.
And since that time, you didn't get any,
One every 10 years. You have to be patient.
So can you comment a bit on the fact that we haven't seen the prompt atmospheric neutrinos? Is this a problem?
No, our limits are, I think, a few factors above where the models would start to break down. So we're just not quite there yet.
So we've seen somewhat less than expected, but the numbers are so low that
In optimistic models, I think, have been ruled out, but more realistic ones have not yet been ruled out. It would be surprising if it weren't there, right? You expect some charm, yeah, right.
Is the deployment of the upgrade or the second generation impacted by the recent NSF announcement about the?
Yeah, so the NSF recently announced that they had to do major renovations of the South Pole Station, and indeed most of the NSF facilities in Antarctica. This has already had an effect on the upgrade, but the upgrade strings will be deployed. We have been promised that by NSF. This will, though, have an impact on Gen 2. It's clearly going to result in a delay of at least a few years in when Gen 2 could be deployed. But Gen 2 hasn't been formally proposed yet. So you can't really call it delayed since it's not being constructed yet or even proposed yet. But it will have an impact for sure. And not a positive one.
So at some point you were mentioning flavor and constraints in your physics, and you were showing a quantum gravity. Can you elaborate on that?
So I can't address the theoretical physics of quantum gravity. That's beyond my knowledge. But there are models of quantum gravity that generally have a differential impact on neutrinos as they travel through space, because the interaction depends on the mass of the neutrino that is traveling. And neutrinos come in 3 different mass eigenstates, and so they are impacted as they travel through space, in principle by quantum gravity. And one way that would be manifested in data seen by IceCube or similar detectors is that certain flavors could be completely suppressed relative to others.
So these are plant suppressed things. So can you give an idea of what type of constraints, the order of magnitude, which type of models is constrained? Or
I don't have any slides on that, but I refer you to this reference here. There are constraints that have been placed by IceCube data, but I don't know what they are off the top of my head.
Yes, can you go to the slide where you show the improvement on the animal sensitivity for the upgrade? Yeah, so on the bottom left for the true normal ordering, there is this thing on the lower octants that is enhanced when you go to the upgrade. On the left, yeah.
Up here, you mean?
Yeah.
Yeah.
Is that a feature of IceCube or?
Yeah, it does look kind of strange. I can't remember the reason for that. I'll have to get back to you on that. I don't remember why that kink appears. It doesn't look physical, I agree.
Yeah, I was wondering because it seems to be enhanced by the upgrade, but.
Yeah, yeah.
Correct.
There is a question on Zoom, I think.
Okay.
Um, What are the considerations on the CO2 emission from the diesel?
No, it's a valid question. So, less so for the upgrade, but more so for IceCube Gen 2, which is going to be a large scale effort. It's going to be a larger effort than the effort was for IceCube. We have sort of a special, well, not special, but an independent working group within the IceCube Gen 2 collaboration that is dedicated to determining ways to save energy in this deployment. And some of the things that we're exploring include wind power at the South Pole, which is in principle plausible nowadays. There's not a lot of wind there. And of course, the conditions are pretty harsh during the winter. But in principle, that could provide or at least offset some of the energy. We used to carry in all the fuel that was used not only to heat buildings there, but also to melt the holes in the ice by airplane. So the airplanes would fly in from the coast, use about 1/3 of the fuel to get to the South Pole, then offload 1/3, and then fly back with the remaining 1/3. And now instead, we use an overland route from McMurdo Station at the coast into the South Pole, and we carry in a lot of fuel that way, which is more efficient. Of course, it still means you're burning fuel. At least getting it there doesn't require burning as much fuel. And there's also the possibility of using solar arrays, although that is really only viable for a few months of the year, because 6 months of the year it's dark, and the rest of the year the sun is fairly low on the horizon, and the weather is not always clear. But it's still possibly something we could use. And we're also going to try to limit the number of trips that people take in order to go to the South Pole to work on IceCube and Gen 2, because each of those trips is, of course, a lot of kilometers to travel. And so limiting that would reduce the carbon dioxide emissions.
So do you know what's the scale in the CO2 that we're talking about?
Compared to what?
How
mean-
many tons?
Oh, how many tons? I don't know that off the top of my head, but we need about 5,000 gallons per 20,000 liters per hole of fuel. I should say one of the things that we have done for a long time is make sure that the holes that we're drilling are as small in diameter as possible. There are some constraints we have to deal with here. We don't want to make the holes so small that when we're in the middle of deploying the strings, it refreezes and prevents us from deploying the rest of the string. The string gets stuck. That has happened once with the predecessor to IceCube called the Mandarin. I was there for that, and it was not a pleasant experience. But we make our modules as small as possible in diameter so that we can make the holes into which they're going to be inserted as small as possible. And as you can imagine, the amount of fuel that's needed to melt the hole goes as the square of the diameter of the hole. So the smaller you can make it, the more fuel you save. So we are obviously going to be doing that as best we can as well.